Ever wonder how your phone's processor talks to its memory? It's not just a simple conversation, it's more like a series of secret handshakes, these really clever tricks that make everything happen at lightning speed. In this explainer, we're going to pull back the curtain on ARM processors and see exactly how they pinpoint data with such incredible precision.
So let's start with the big question. How does a processor actually find what it's looking for? I mean, think about it. Memory's like this colossal library with billions and billions of books. How does the processor not just find the right book, but the exact page and the specific word it needs, all in a fraction of a second? Well, that's the whole problem that addressing modes were invented to solve.
All right, here's our game plan for cracking this code. We'll start with the one single rule that basically governs everything. Then we'll meet the key instructions that do all the heavy lifting. After that, we'll dive into the 3 main handshakes for finding data, see how they're used out in the real world, and then we'll wrap it all up by solving a little puzzle to put everything together.
Okay, before we can even think about finding data, we have to understand the absolute golden rule of ARM processors. It's something called a load-store architecture, and honestly, it's a really simple idea, but it's profound, and it changes how absolutely everything works.
The best way to think about it is like this. The CPU, the processor, it's like a high-tech workshop. And you can't work on your materials while they're still sitting on the warehouse shelf. That shelf is the memory. Nope. You first have to load them onto your workbench. And that workbench is a set of super fast little storage spots called registers. Only then, once the data is in a register, can you actually do your work on it.
So, if all the real work happens on the workbench, how do we get our materials from the warehouse in the first place, and then how do we put them back when we're done? Well, that's where 2 absolutely essential commands come into play. These are the heavy lifters of the entire operation.
It's really just a simple two-way street. You have LDR, which stands for load, and that pulls data from memory into one of those registers. And then you have STR for store, which does the opposite. It pushes data from a register back into memory. So in these examples you see here, the address we care about is being held in register R1, and the actual data is moving to or from register R0. Simple as that.
Okay, but here's where it gets really, really clever. Specifying that memory address, the part inside the square brackets, it isn't always as simple as just pointing to a single register. ARM gives us a few really flexible ways to do this, and these are what it calls indexing modes.
This simple formula right here is the key to everything. The final address, what we call the effective address, is calculated from a base register plus or minus some kind of offset. The analogy is perfect. It's exactly like having a bookmark in a book. That's your base, and knowing the info you need is, say, 4 pages ahead. That's your offset.
So first up is a mode that is absolutely perfect for stepping through a list of data, one piece at a time. The logic is dead simple. You figure out the new address, you go access the memory right there, and then you update your bookmark to that new spot, so you're ready for the next one. This is called pre-indexed addressing with writeback.
Now, see that exclamation mark at the end of the line? That is the secret sauce. It's basically a direct order to the processor that says, hey, first, calculate the new address. That's R1 plus 4. Second, go grab the data from that new spot. And third, and this is the writeback part, update R1 to this new address, so we're all set for the next time through the loop. It does all 3 of those steps in one single efficient instruction.
But what if you just want to, peek at some data a few pages ahead without actually moving your bookmark? Maybe you just need to check a value without losing your current spot. For that, you use the exact same syntax, but you just leave off the exclamation mark. The processor still calculates R1 plus 4 to find and load the data. But, and this is the key, it does not modify R1. Your original bookmark stays exactly where it was.
All right, our third and final method is called post-indexed addressing, and this one flips the whole order of operations completely. It's a subtle difference, but it's incredibly powerful.
Now, pay close attention to the syntax here. See how the offset, the #4, is now outside the brackets? That tells the processor something completely different. It says, first, use the address I already have in R1 and load that data. Then, after you've safely got the data, you can go ahead and update R1 by adding 4 to it to get it ready for the next operation. So we act on our current location first, and then we move.
So let's just break it all down side by side. It really just comes down to answering 2 simple questions. 1, do you calculate the new address before or after you access the memory? And 2, do you permanently update your bookmark, that base register, or not? These 3 modes give you precise control over both of those things.
So you might be thinking, why have 3 different ways to do what is basically the same thing? Well, it's all about efficiency. Different programming tasks just benefit from different approaches. Let's take a look at a few really common applications.
I mean, these modes are the absolute workhorses of everyday programming. You're looping through an array of data? Pre-indexed with writeback is perfect because it automatically moves you to the next element. Are you managing a program stack? Well, post-indexing is often used there to pop a value off the stack first and then update the stack pointer. It's all about using the right tool for the job to make your code as efficient as possible.
Okay, theory is great and all, but let's make this really concrete. We're going to trace 3 simple instructions and watch exactly how they change the values in our registers and memory. I promise you, this is the part where it all clicks into place.
So here's our setup. And hey, don't worry about the 0x in front of the numbers. That just means they're in hexadecimal, which is just a common way to write down memory addresses. All we really need to know is that register R1 starts out by pointing to address 9000. Our goal is to just track what happens to the values in the registers after we execute 3 different load instructions. First up, LDR R0 from R1 #4. Okay, this is pre-indexed with writeback. So the processor first calculates the new address. 9000 plus 4 equals 9004. It then goes to that address, grabs the value, which is 2222222, and loads it into R0. And because of that exclamation mark, it updates R1 to the new address, 9004. Done. All right, next, a really simple load, LDR R2 R1. This is the most basic form you can have. It just looks at the current value of R1, which is now 9004, remember? And it loads the data from there into a new register, R2. Since there's no offset and no writeback, R1 stays exactly where it is. And for the finale, LDR R3, R1 #4. This is our post-index mode, so remember the rule. It accesses memory first. The processor uses R1's current address, still 9004, to load the value into R3. After that's all done and the data is safe, then it updates R1 by adding 4. So R1 ends its journey at 9008, but R3 was loaded using the old address.
So you can really see that each mode is a specialized tool. Pre-indexing is like deciding where you're going to go before you act. Post-indexing is all about dealing with what's right in front of you first and then deciding where to go next, which leads to one final thought for you. If pre-indexing is so perfect for reading through a list, when would you ever want to grab an item off a pile first and only then update your idea of where the top of that pile is? That's the kind of subtle optimization that makes code really fast. It's all about choosing the right secret handshake for the right job.